In applied data science, we rarely have access to the absolute truth of an entire population. Instead, we have to predict the behavior of millions using only a tiny, isolated fraction of data. To see what happens when that scaling process breaks down, we can look at the 1936 U.S. presidential election. The Literary Digest, a popular magazine, ran a massive exit poll to predict the winner. They mailed out 10 million surveys and received an astounding 2.27 million responses, primarily measuring support for Republican candidate Alf Landon. Based on this massive dataset, the magazine predicted that Landon would win the presidency in an absolute landslide. The exact opposite happened. Franklin D. Roosevelt defeated Landon in one of the most overwhelming electoral victories in American history. How could a prediction backed by over 2 million data points fail completely? The error was in the mailing list. The magazine sourced its 10 million survey targets from 3 specific registries: registered car owners, magazine subscribers, and telephone owners. In 1936, during the Great Depression, owning a car or a telephone meant you were relatively wealthy. The sample filtered out the working-class citizens who made up the majority of the country and who overwhelmingly voted for Roosevelt. This is selection bias. Having a huge amount of data is mathematically useless if your sample does not accurately reflect the diversity of your actual population. Before we can apply advanced mathematics to predict outcomes, we must secure a truly representative sample. Once we have that, we can build the statistical engine of inference. Let's apply this to a modern business problem. Imagine Atlic Solar Panels wants to enter the Indian market. They are targeting 12 million households and need to find the average monthly electricity bill. Surveying all 12 million households to find the true population parameter is financially impossible. Instead, researchers deploy a targeted sampling strategy. They visit 207 different cities, collecting a random sample of 50 household bills in each location. This chart shows the distribution of individual electricity bills from one city. The shape is chaotic and right-skewed, stretched by a few mansions with massive energy consumption. To find the signal in this noise, we stop looking at individual bills. Instead, we calculate the mathematical average, the mean, for each of the 207 small samples. Plotting those 207 averages onto a new chart, the data stacks up symmetrically. This is the Central Limit Theorem. With a sample size of 30 or more, sample means always form a normal bell curve, regardless of the original population skew. Because this curve is a mathematically perfect normal distribution, we can use established laws of probability to measure the standard error and pinpoint the true population mean. The Central Limit Theorem acts as the bridge that allows data scientists to move from a small sample to a statistically sound prediction of the entire population. We can translate this normal curve into a tool for making decisions through hypothesis testing. Suppose the New Jersey government publishes a report claiming local housing inflation is exactly 10%, but your own neighborhood observations suggest it is significantly higher. We formulate a statistical test to challenge this. We define the null hypothesis as the status quo, assuming the government's 10% claim is true. The alternate hypothesis is your specific claim, that inflation is strictly greater than 10%. Statistics operates on a judicial framework. Just like a courtroom assumes a suspect is innocent until proven guilty, data science assumes the null hypothesis is true until the data provides overwhelming mathematical evidence to reject it. On a standard normal curve centered at 10, we set our significance level, alpha, at 5%. The extreme right tail forms our rejection region. The exact line separating random fluctuations from statistical significance is the z-critical boundary, located 1.645 standard deviations away. You survey 100 houses and find an average inflation of 11%. Running this through the standard error formula gives us a sample z-score of 2.5. When we compare our sample z-score, it maps to 2.5, landing deep inside the red rejection region. Because the sample landed in the rejection region, the deviation is mathematically too extreme to be random chance. We reject the null hypothesis and prove the government's report is incorrect. There is a major caveat to the z-test. It strictly requires knowing the true population variance and having a sample size of at least 30 to guarantee that perfect normal curve. how do we prove claims when data is scarce? Like if a school tests a new teaching method on a single classroom of 20 students. Small samples carry massive variance. A class of 20 students is highly susceptible to random luck, meaning the strict rules of the z-test no longer safely apply. The mathematical solution for small sample sizes is students' t-distribution, developed by a statistician publishing under a pen name while working at the Guinness Brewery. This diagram illustrates the physical difference of the t-distribution curve. It resembles a bell curve, but it is flatter in the middle, with distinctly fatter tails. These fatter tails mean the mathematical model naturally accounts for a higher probability of extreme values occurring purely by random chance in small groups. Because the tails are fatter, the critical boundary is pushed further out. A t-test demands a much more extreme result to confidently reject the null hypothesis. Hypothesis testing is certainly not a one-size-fits-all mathematical formula. Data scientists must dynamically select their statistical engine based entirely on the size and shape of the data they are analyzing. The corporate application for a data scientist often involves testing a new machine learning algorithm or launching a product, like Phase 2 of the Atlico Bank credit card. One major mistake is comparing your new product's performance against historical data from last year. This is a one-sample test that fails in a business environment. If sales increase over historical baselines, you cannot prove the new product was the cause. The jump could be driven by a seasonal shift, a marketing promo, or an external global event. The industry solution is the A/B test, or two-sample test. It is designed to completely isolate the product from external market noise. We divide our live users, we run a control group experiencing the old product, alongside a test group experiencing the new product at the exact same time. For Atlico Bank, we test a specific hypothesis. Does the new credit card generate a strictly higher average daily transaction amount for the 18 to 25 demographic? This methodology comes from its strictest application, medical clinical trials, where double-blinded control and test groups are used to remove both external variables and human psychological bias. A properly designed A/B test is the only scientific way to prove that a specific product change caused a shift in user behavior. Returning to the Atlico Bank rollout, the business manager pushes back before launch due to budget constraints. They demand to know the absolute minimum number of users required for the A/B test. Data scientists solve this resource constraint by balancing statistical power, the ability to correctly catch a real effect, with effect size. Effect size measures practical significance. A test might prove a 1% increase in sales is statistically real, but the business only cares if the increase is large enough to be profitable. To detect a meaningful effect size of 0.4 standard deviations without risking a false negative, the math dictates we need exactly 40 users in both the control and test groups. After 2 months, the data is collected. The control group averaged $221.18 per transaction, while the test group on the new card averaged $235.98. This formula calculates the final metric. It yields a z-score of 2.74, which directly translates into a p-value of 0.003. We translate this p-value for the executive board. The math proves there is less than a 1% chance that this $14.80 increase in revenue was just a random fluke. Hypothesis testing translates abstract probability into a risk-quantified business decision, providing the statistical confidence required for a global launch.